Look at this. Thousands of birds moving as one single organism. No leader, no plan, no communication tower, just pure instinct.
How do they do it? How does a flock move so perfectly without a conductor?
The answer is one of the most elegant ideas in computer science. 3 simple rules that create breathtaking complexity. This is the story of the Boids algorithm, and how 3 lines of math can simulate nature itself. Let's fly in. Every autumn, millions of starlings gather in the sky over Rome. They form massive swirling clouds called murmurations. Each bird reacts in milliseconds, turning, diving, rising together. No single bird leads. The flock has no brain, no center. And it's not just birds. Fish form schools that move like liquid silver. Ants march in organized columns without any map. Bees swarm in perfect rotating spheres around their queen. Even bacteria cluster together in synchronized colonies. For centuries, scientists assumed there must be a leader. But the truth is far more beautiful. There is no leader at all. In 1986, a computer graphics researcher named Craig Reynolds had an idea.
What if flocking behavior wasn't directed from the top down? What if it emerged from the bottom up, from simple individual rules?
He created a simulation called Boids, short for birdoids. Each Boid was an independent agent with no global knowledge. It didn't know about the whole flock, only its nearby neighbors. And with just 3 rules, the Boids formed realistic flocks. No scripted paths, no pre-planned formations.
The magic happened on its own. This is called emergent behavior.
Let's break down those 3 rules one at a time. Rule number 1, separation. Don't crash into your neighbors. Each Boid looks around and checks how close its neighbors are. If another Boid is too close, it steers away. The closer the neighbor, the stronger the push to move apart. Think of it like personal space. Everyone needs some room. Without separation, the flock would collapse into a single point. Every Boid would pile on top of every other Boid. Total chaos. But with this rule, they spread out naturally.
Creating that beautiful distributed cloud shape we see in nature.
Separation prevents collision. It gives the flock its volume. But separation alone would scatter everyone apart. We need more rules. Rule number 2, alignment. Fly in the same direction as your neighbors. Each Boid looks at the average heading of nearby Boids. Then it adjusts its own direction to match that average. If your neighbors are heading north, you steer a bit north too. This creates the coordinated flow we see in real flocks. Without alignment, the flock would just be a scattered cloud. Boids would move in random directions, bouncing off each other. Alignment is what turns a crowd into a coordinated flock. It's the rule that makes everyone fly together, not just near each other. Now the Boids move apart but in the same direction. Still not enough. We need one more rule to hold the flock together. Rule number 3, cohesion. Stay close to the group. Each Boid calculates the center of mass of its nearby neighbors. Then it steers gently toward that center point. Not a hard pull, just a soft nudge toward the average position. Without cohesion, the flock would drift apart and dissolve. Each Boid would wander off on its own separate trajectory. But cohesion keeps them bonded. It creates the flock's overall shape. Think of it like gravity, a gentle force pulling everyone inward. Not strong enough to crush them, that's what separation prevents, but strong enough to keep the group from falling apart entirely.
Now we have all 3 rules. Let's see what happens when we combine them. Here's where the magic happens. Separation plus alignment plus cohesion.
Each Boid calculates all 3 forces at every single frame. The forces are weighted and added together into one steering vector. Then the Boid adjusts its velocity accordingly.
Watch, starting from random positions and random directions.
Within seconds, order emerges from total chaos. Small clusters form first. Then they merge into flowing streams.
The streams curve and twist, forming that unmistakable flock shape.
No Boyd knows the big picture. Each one only follows 3 simple rules. Yet the whole group behaves like a single intelligent organism. This is emergence, true complexity arising from pure simplicity. The weights of the 3 rules change the flock's entire personality. If we increase separation strength, the flock becomes loose and spread out, like a relaxed group of friends walking through a park. If we increase alignment, the flock becomes a tight, disciplined formation, like a military squadron flying in perfect synchronized lines. If we increase cohesion, the flock becomes a dense, tight ball, like a school of fish being chased by a hungry predator. And perception range matters too. How far can each Boyd see? A short range means small, tight subgroups that move independently. A long range means the whole flock moves as one unified mass. By tuning these parameters, we can simulate almost any flocking behavior. In nature, different species use different weightings of these same rules. Starlings have strong alignment and cohesion. Their murmurations are tight. Fish schools prioritize separation when threatened. They explode outward. Then cohesion pulls them back together once the danger passes. Locust swarms are driven mainly by alignment, a devastating wave. Even human crowds follow similar patterns in pedestrian simulations. When people walk in a busy street, they unconsciously separate and align. They avoid collisions, match walking speed, and follow the general flow. The same 3 rules, playing out across millions of species every day. Nature discovered this algorithm long before any computer did. Reynolds just figured out how to write it down in code. The Boids algorithm revolutionized computer animation. The 1992 film Batman Returns used it for its Penguin Army March. Finding Nemo used flocking for its massive fish school scenes. Lord of the Rings used a system called Massive for its epic battle scenes. Thousands of digital warriors, each following simple local rules. Beyond movies, drone swarms use Boyd-like algorithms for coordination. Self-driving cars use separation and alignment to navigate traffic. Robot swarms for search and rescue apply all 3 rules. Even network routing protocols are inspired by flocking behavior. One algorithm, invented for fun, now powers real-world technology.
The deeper lesson of Boids is about emergence itself.
Simple rules, followed by many agents, create complex systems. No master plan, no central controller, no blueprint for the flock. The intelligence lives in the interaction, not in any single individual. This idea echoes through all of nature and science. Brain cells follow simple rules, yet somehow consciousness emerges. Market traders follow self-interest, yet economies form complex patterns.
Emergence is everywhere around us. Boyd's just made it beautifully visible. So here's what we've learned about the flocking algorithm.
Separation keeps Boids from colliding with each other. Alignment makes them fly in the same direction as a group. Cohesion holds the flock together as one unified shape.
3 rules, no leader, infinite complexity.
From starlings in Rome to digital armies on the big screen.
One simple idea that unlocked the secret of collective behavior.